welcome to the second part of the definition and classification of energy storage systems lecture. In that diagram, known as the Ragone diagram, we see many different energy storages, and these diagrams are typically used to explain for which application which storages are used for. On the horizontal line we have typical storage capacities of stores, starting from a few watt hours to kilowatt, megawatt hours up to terawatt hours. On the vertical we have the duration of discharge, starting in milliseconds and again in a logarithmic scale, reaching over minutes, hours, days, weeks, months up to years. And typically what we see on the left lower part of the diagram is the pure electrical stores. Almost no energy content, is only used for a few milliseconds to seconds, as typically for stability reasons in electric grids. Then we come more to the hourly to daily, and that is the typical application of battery systems and also sensible thermal heat systems. And at the more right we come into the diagram, then we more come to the chemical energy systems, either liquid chemical or gaseous chemical systems. Having more discussion, how could different energy stores help us to interlink different energy sectors? And starting with the electric energy storage systems, it is mainly the pure power sector, reaching, for example, with capacitors, also in a few applications in the mobility sector. When we talk about electrochemical energy systems, so the typical batteries, again, they are applied in the electrical, in the power sector, but when thinking on electric cars, then they also have a strong involvement in the mobility sector. Discussing the mechanical stores, then again the power sector, when we think on the pumped hydro storages or the compressed air energy storage, is the pure power sector, but again there are some maybe exceptions when thinking on flywheels in tramway systems. Also they have their part in the mobility sector. Coming for thermal energy storage systems, then sure, they have their impact in the heat sector, but when talking about power to heat, they also link power and the heating sector. The pure chemical energy stores, when thinking on the pure fuel stores, the fuel storage tanks, then it's mainly only the mobility sector. But when thinking on power to gas, power to liquid, then they involve all the sectors, power, heat and mobility, where they have their strengths. And then quite often neglected, but the same task, then the energy storage, is just shifting loads or the demand side management. And demand side management, that can be done in the power sector, in the heating sector and also in the transportation sector. Coming to another comparison, and that is what we have here on the horizontal, is just the volumetric energy density in kilowatt hours per cubic meter. On the vertical we have the efficiency of typical storage systems in percent, and then the area of those circles we see that is the typical investment cost of a storage system. And when we start with that big area, that big blue area, that is an exceptional position. It is the pure electrical systems like capacitors. So they have the highest efficiency of all stores, but the lowest energy density, and you see the costs is tremendous. So they are not really used to store energy, they are more used to deliver for a short time a quite high power. That is their application, their field of application. When coming to the electrochemical stores, the costs, you can see already, is much smaller than the pure electrical, but compared to the other stores we see here on this slide, they are still quite high, very high. But they have high efficiencies too, and have quite a wide range of energy densities. When we look to the mechanical stores, we see on the complete left side, also with high efficiency, but what is very good, also quite low costs, is the traditional pumped hydro storage system. Compressed energy air has a quite low efficiency, and the flywheel storage has again very high costs. Coming now to the thermal stores, and again here we see how interesting it is to couple different energy sectors. And I made two circles around the sensitive heat storage systems, because that dot is so small that you even cannot see it. That means the cost of that old-fashioned hot water tank is so small, you cannot imagine any price decrease in battery technology that they can reach a similar price even in the far future. So whenever we are able to combine the power sector and the thermal sector by solving the storage problem on the thermal side, we always have the biggest advantage. Even latent heat or thermochemical storage, the cost is small compared to electrical stores, for example. And then coming to the other extreme that we find on the complete right side of the diagram and the complete bottom of the diagram is the gas storage for hydrogen or for methane, for natural gas. And here the dots are even smaller than with the heat storage, but what we see, they have a big advantage, and that is the enormous volumetric energy density, but they have the very big disadvantage, and that is the very low efficiency when going from electricity via gas storage to electricity back again. And to be honest, the small dots only cover the storage, but the conversion technology for electrolysis, methanization, that is quite expensive, what is not taken here into account in this graph. Ending with some questions you might answer, maybe not only with the slides here, but also with the script. So what is the difference between a primary and a secondary energy storage? What means sectoral and cross-sectoral energy storage? What are the 5 types of energy storage systems by means of physical energy form? Give 3 examples of low temperature batteries. Which parameters influence the economic performance of energy storage systems? In which sectors electrical, electrochemical, mechanical, chemical and thermal storages can be applied? Give examples. And in which sectors demand response activities can have the same function as energy storage systems? Thank you very much.